I want to compare the citric acid cycle, which is in cellular respiration, with the Calvin cycle, which is part of photosynthesis. So both of them are cycles, which means they start and end with the same molecule. And we're not super detailed in the steps of the cycles, but it is important to see that they have similarities, but they're sort of like the complete opposite in the end. Okay, so this is the Calvin cycle in photosynthesis. These little circles or balls are representing a carbon compound. So they have oxygens and hydrogens on the carbons, but basically this is just showing us there is a 1, 2, 3, 4, 5 carbon compound, and we're just going to call it our starter molecule. It's actually RuBP, ribulose 1,5 bisphosphate, but for our purposes, I'm not too worried about that. Okay, so from the starter in the Calvin cycle, we are going to be building a carbon compound. So we need to bring some carbons in it to build. So we're going to bring carbon in the form of CO2. So that's going to come into the cycle and be added on to the 5 carbon compound. It's added on here. This is a brief state that's basically unstable that breaks in half pretty quickly. Not too concerned about the details there, but just to be accurate. But you see, basically, we've brought in this carbon in the form of carbon dioxide and fixed it, which means attached it to the starter molecule. So we can call this stage here is that we're going to be building the carbon compound. Then, in order to build, we need to put some energy into the system because building is an anabolic process. And the way we're going to do that is using ATP. And remember, a key point here is that with ATP, often what you do is you add the phosphate to make the molecule unstable, and then you switch it out for what you want. So I'm just going to draw it like this. We're skipping a bunch of steps there. But we're going to take our ATP, and we're going to add that phosphate in, so it leaves as ADP. Make that carbon compound reactive. So I'm going to draw a wiggly bond. There's the phosphate on the end. This is a reactive molecule now. And then we're going to switch it out for what we really want. And you'll notice this is using energy. Let's box that. Okay. We're going to switch it out for what we really want to embed in the molecule, which are our electrons, because we're trying to make a molecule that has a lot of stored energy, and those electrons in the bonds can do that. So we have NADP come in. This is actually from the light reactions, and it leaves as NADP plus because it's dropping off the electrons into the carbon compound. And what did we do? We switched out the phosphate group that we had added. This phosphate group gets added here. We bumped it off and added the electrons instead. That's like how I think of it. Okay, there's some steps, and then we end up with this molecule here, which is our G3P. But the most important part of this is that is our product that we're looking for. So this is what I often refer to as the carbon compound. So organic molecule, technically G3P is its name, glyceraldehyde 3-phosphate, to use in the cell. Whether that it usually gets built into glucose, can be built into sucrose to move around the plant body. So we've made our carbon compound, that's the goal. And then we have a number of steps here which are going to regenerate the starter molecule so the cycle can go again. So if I had to describe what's happening here, the overall goal is that we are embedding electrons in a carbon compound, organic molecule, making that high energy molecule. Let's compare that to the cellular respiration cycle, the citric acid cycle. It also starts with a starter molecule. In this case, it's a 4-carbon compound called oxaloacetate, but we'll just think of it as our starter molecule. And then that is going to have a similar process actually happen to it here, but for different overall purpose, but we're going to have some carbon come in and get added to that starter molecule. So it's coming in the form of acetyl-CoA. I draw this wiggly bond with this coenzyme A because it makes the acetyl-CoA unstable. It makes it reactive. And that's what we're doing. We're switching out the CoA, the coenzyme A, and adding the 2 carbons onto this starter molecule. So it'll actually be like this. Okay. All right, great. So we've got some new carbons in. Now we're not trying to build this time like we did in the Calvin cycle. This time we're trying to extract electrons. So we need more carbons in there so we have more electrons to basically extract. Those carbons come from food originally. I'm going to draw a simple version of this cycle. So what's happening? We are extracting electrons. So what do? We're going to break a bond. Remember, that's one of our things. Break a bond, extract electrons. We're going to break a bond that's going to pop off a CO2. And we're breaking down, right? So this time we're breaking down instead of building. The opposite of the Calvin cycle. So we break off a CO2, we've broken a bond, which means we can extract electrons. This is in cellular respiration, so our CAB that comes in is NAD+. It's going to take those electrons away, so these electrons are going out of the being extracted from the carbon compound and leaving at NADH. Then we're going to do that again. Pop off another CO2. Extract some more electrons. Electrons are coming out of the carbon compound. Okay. So we've extracted electrons. Now, before we were using ATP, in this case, we're going to make a little ATP. So it's ADP is going to be able to be made into ATP. So we're making it instead of using it like we did in the Calvin cycle. And then we're going to be able to extract some more electrons. There's the FAD version other electron carrier to make FADH2. So that's more electrons leaving, being extracted from the carbon compound. And then we have another NAD+ come in, take those electrons away as NADH. More electrons being extracted from that carbon compound. Okay. And then during that process there, we are regenerating the starter molecule. If I had to say the overall purpose of the citric acid cycle, I'd say it's to extract electrons from a carbon compound, organic molecule. So to compare the Calvin cycle to the citric acid cycle, you can see their opposite purposes: embedding electrons in a carbon compound in the Calvin cycle in photosynthesis, extracting electrons from a carbon compound in the citric acid cycle in cellular respiration. It is a building overall process in the Calvin cycle versus an extracting or breaking down process in the citric acid cycle. It is using ATP energy in the Calvin cycle, which makes sense because if it's a building process, we'd expect that, versus a breaking down, which we are able to make some ATP to store energy in the Calvin cycle. It is embedding electrons. Electrons go into the carbon compound in the Calvin cycle. It is extracting electrons. Electrons go out in the citric acid cycle. We are making a carbon compound in the Calvin cycle. We are breaking it down overall in the citric acid cycle. Both of them end up having a starter molecule that is the beginning and then regenerated at the end. So that is similar between them. And that's the comparison between the citric acid cycle and the Calvin cycle.